So the idea is kind of remarkably simple for something that sounds really difficult. What I want to try to do is something different than what we've done. I don't want to find the area under a function. I actually want to know how long is this from A to B? What's the length of this? And if you think about it for a minute, it's like, holy shit, how the hell would we freaking do that? Right? You guys understand the idea here, right? If it's a straight line, easy. I can do that, no problem. In fact, if it was this, let's say, let's give a specific 1, 2, 5. What you got, Jeff? 6, sure. Can somebody tell me how long that is? Thank God you don't have to bring in square root. You still have to bring in. What do you say? Square root of -2? When in doubt, bring out the imaginary shit. It's imaginary. Come on, guys. Come on. You're making me cry.
8 squared plus b squared.
Yes, the Pythagorean theorem is a good idea.
4.
Root square root?
Root 32.
Yeah. See, I thought I was making fun of me.
I thought you said root -2.
Oh, no.
All right.
32.
So you got 4 squared plus 4 squared. You're fine.
If you check your accounts so fast with my hand, look at something else.
I did -2. I thought you were just being. And of course, you can simplify that. But the important thing is, that's the formula I'm going to use over here somehow. And the difference is, obviously, this is not straight everywhere. But if I zoom in enough, the whole idea of that linearity section we did, right, doing the. The more you zoom into a continuous differentiable function, the more straight it looks. Just like the closer you get to the surface of the Earth, the more flat it looks when we actually know it's not. You guys are with me on this, right? I mean, we've done this before. This idea of the more I zoom in to it's got to be continuous and differentiable. If I zoom in, it's going to look like a straight line. That's the whole idea of derivative. That's why the derivative makes sense. At that instant, it is heading a certain direction, which must mean it looks like a line, which allows us to do stuff like finding tangent lines, which is related to linear approximations. All right. How are we doing there? Does that sound familiar? Hopefully.
Some of those words
Some of those words sound familiar. Okay. So, much like we did, if I wanted to find the area, I would break this up into little triangles, rectangles, and then add them together. You can use trapezoids and stuff. You'll learn about that later. If you take any more calculus. I'm going to break this up into little segments, line segments. The smaller they are, the better. So that's my approximation right there. From A to A plus delta X. So this little triangle, how big is this side? Delta X. And what's this? Delta Y. There it is. I like it. Let me stop there for a second. So the idea then is I'm going to allow these to get infinitely small, right? So the limiting process still. Again, we're not going to get delved too deep into that. But that's the idea. Because the smaller this gets, the more linear it gets, the more sense this makes what I'm going to use. Well, how long is that little line segment?
The square root of x squared, y squared, change.
Delta x squared.
I like it, right? That's that one little segment. The ith segment. Okay, cool. So I want to sum these up. So let me call this little, this doesn't really matter right now. This little one, because for different ones, it's going to be a different delta y. Does that make sense? Because like from here to here, the y doesn't change as much as it did here. So that's why a little yi, I got to put an I there somewhere. And I'm going to sum this up from I equals 1 to infinity, basically, right? All right, let me stop here. You're not going to have to do this yourself, but this should look very familiar. This idea. So instead of adding up areas of rectangles, I'm adding up lengths of line segments. I like it. So what must be true about this function in order for me to be able to do this?
Continuous.
Differentiable.
Kick ass. Continuous differentiable. Those two happen in so many different theorems, it's crazy. If If you have a continuous and differentiable function, you can do a lot of shit with it. If it ain't, it can do a lot of weird shit. Alright. So this is kind of cool the way this works. How do I say this? So normally I'd have an integral, but I need like a dx out here. So can we factor out a delta x? Yes, we can. Believe it or not. Stay with me now. Let me do a little example. Can you factor out an x all day long? Totally. You totally can. Right? Isn't this square root of x squared times what? I'll start off 1 plus
4 over x squared.
Alright, was that hard? No. And then what's square root of x squared? We'll assume it's positive. Alright, so I'm going to do the same kind of thing we just did there. Now why would this be helpful? Because maybe I'm going to use this in a limit or something, or maybe the x cancels, whatever. So here, I'm going to do the same thing. Take out a delta x. Square root of delta x squared is delta x. It's going to end up being 1 plus this over delta x squared, the same way. Alright? And do you see what I'm trying to do? I'm trying to make it look more like limit sum blah delta x, because that looks more like intervals function delta x dx, right? So I get square root of 1 plus delta yi over delta x becoming delta squared, or yeah, delta x. So I pull that out. And now what is change in y over change in x?
dy dx.
Which is the derivative of the function. There it is. At a point. So the limit that the n goes to infinity, this becomes exactly equal to f prime at that xi that I'm looking at. So here's what happens. This is almost too good to believe. This is relatively easy based on stuff we've done already. Looks vaguely familiar, but is nowhere near as detailed. So this becomes the integral from a to b, square root of 1 plus f prime of x squared dx. Applying the limit, that's what happens to everything. The deltas become d's, so dy dx is another way to say f prime. You can even leave it dy dx if you want to, I like it. Just make it look more like what the book's got. So given some function like, let's say f of x is x cubed minus 4x squared. And I want to know how long that is from, I don't care, 1 to 4. What does this integral need in order for it to be done? I have to first figure out what f prime is. So what's f prime?
3x squared minus 8x.
Throw that bad boy in here. Integral from 1 to 4. Square root of 1 plus squared, right? This is page 539. I'm doing section 8.1. Oh, they do write it the other way. Good.
That looks reasonable now.
Yeah, I know, it's crazy. The only bad part is sort of like washers and stuff, you have squares on the stuff, so depending on how ugly your function gets or its derivative gets, you have to FOIL out more and more and more, but still. I mean, if that's the problem, you're like, well, that could be a lot worse than that. Shit, yeah, I'm going to do that. That's easy. So you just FOIL it out. I've lost interest now.
Minus 48x cubed.
Yes, 48x squared plus 64. I'm sorry, this is
That's cubed.
cubed
Yeah. And then x squared.
squared dx. Now, what do you notice that's kind of rough with these, though? They're going to have to give us certain ones that work nice. So this problem, I mean, what's the major issue with this kind of problem? There's a big old square root, right? So this problem, this one I could actually not do. I mean, I could do this in different ways. I have Calc 2, we could do this. So in this homework, they're going to give me functions here that'll actually make it work well. Maybe this will factor so that it becomes something squared. So then the square root can kill that square. I mean, they got to do something to get rid of the square root. Because we cannot handle, I can't do this. This looks very simple, but I can't do that. Why not? What's missing? What could I put in there that would make this doable for us? Yeah, if I put an x out here, then I could do it. Because now the derivative of this is there. That's what you're looking for u sub. Why do I know this won't work? Because the inside function's derivative is not there. Yeah.
Couldn't you like distribute the 1/2 to both things, to both?
Oh, hell no. So that's like saying 3 plus 5 squared equals 9 plus 25 equals 34. So 8 squared is 34. Right? Okay. So if it's a 1/2 power, it works like all powers. That kind of thing don't work. I like it. And not to pickle and destroy at all, but that's the thing that a lot of guys still do. That just makes me cry. It makes me cry. I don't actually cry, but I get close. I mean, this should just hurt. That hurt me to write that. I pretended like it was an equation, because you could solve this and figure out what x's make this work. But does this work in general? Hell no. Because square roots do not work well with subtraction. The same reason why a plus b squared is not a squared plus b squared. It's the exact same reason, exactly the same. Okay. That kind of thing kills me.
Just curious, in the limit, on that bottom equation, how does it capture the a to b?
Oh, so remember, the a to b would be captured by how you define delta x. Right? And the same thing we saw before was, this is a better notation because you actually can see the a to b. But your width is going to be what is affected by what a and b are. Right? So you might remember that from when we were doing that game. Oh, no, okay. Look back and they had the same issue before. Yeah.
Don't we do that with triangle?
What's
That's
that?
on the square root 1 minus x squared with a triangle.
How do you mean?
I mean, like drawing triangle and using tangent or something like an angle.
So one of the things you learn in Calc 2 that we don't know yet, and I might as well show you something right now. Real quick. What if you let x be sine theta?
Let speed 1.
Say again?
Can we let that speed 1?
Sure, but it won't do shit for you. So the thing you got to get over, the thing that I understand when my algebra students have trouble with it, but you should not have any trouble with it. If there's something I don't know, I can call it whatever the hell I want to. That's the whole idea of algebra, isn't it? I don't know what it is. Let's call it x. So if anybody has an issue with that, good God, you're in the wrong place. Right? We should be completely cool with the fact that I want to give it a name so I can do shit to it. Well, then I'm saying here, well, let me give it a better name. That's all I'm saying. I don't know what x is, but let me call it sine. Why isn't it? What's the biggest x could be?
1.
1. What's the smallest it could be? Negative 1. Isn't that what sine does? Ooh. So letting x be sine theta is not changing anything. I'm just changing. I don't want to use the symbol x to represent this thing I don't know. I want to use the symbol sine theta. Who gives a shit? It's just a variable, right? Sine theta is a variable. As theta changes, sine theta changes. That sine theta is a variable. So what's dx? What's dx? If x is sine theta, what's dx? Don't overthink it.
Cosine.
Everybody's saying negative, but it's not negative. Not integration, right? This is neat. This is kind of like the opposite of u sub. I'm not letting u equal some function of x. I'm letting x equal some function of u. I'm using theta because it's trig. But what happens here? Watch. What happens here? What's x? So this would be 1 minus sine squared theta. That should look very familiar. Times dx, which is cosine theta d theta. What's this?
Cosine.
Yeah, cosine squared is cosine, so I get integral cosine squared. And then you can actually, I don't know if you guys remember, there's a trig identity to lower the power of this, right? That's enough for now. Because I've just done part of Calc 2 with you, but this is exactly related to u sub. I think this is what you were going in the direction of, right? Alright. So here, I mean, there's let's see if I remember it. 1 plus Oh, Jeff, do you remember it?
Sine.
No, it's 1 plus
Oh.
cosine.
Two.
Yeah, what was it, Jeff? I can't remember. 2 theta over
2.
4 or something. I can't remember. That sounds vaguely familiar. And sine would be minus, I think. Anyway, it's been a little too long. I just remember that guy. All right, that was beyond anything that we have to worry about for this semester. Cool. That's all I wanted to say about 8.1. Did I assign anything out of 8.1? I said to be announced, right? All right, so it's extra credit, but if you want to do the extra credit, it would be 8.1, say 7 through 11.
Thank you.
Yeah, you're welcome. Jump on that.
Extra credit quiz.
There might be an extra credit question on the final. Yeah,
Like 50 points, right?
total out of 5,000.
Makes up for the whole.
If you do well in this extra credit, you don't have 25.
All right, that's all I got. That's early, but that's fine. So tomorrow and Thursday is focused on review for the final. Yeah.